I'm going to solve this problem a couple of different ways. The first is as suggested using sines and cosines. So I'm going to rewrite this as 2 plus the tangent of x is the sine of x over the cosine x. So tangent squared is the square of that. But when you square a fraction, you just square the numerator and you square the denominator. So that turns into this. Likewise, the secant squared, well, the secant of x is 1 over the cosine of x. So this would be 1 squared over the cosine squared of x, right? Minus 1. So that is equal to this. At this stage, I would move this 1 over because it's in my way. I'm going to multiply by 1 here. Again, I look at the denominators. This has a denominator of 1. This is denominator cosine squared. This has a denominator cosine squared. So I'm going to multiply top and bottom here by cosine squared x. This is multiplying by 1, doesn't change the value. And I'm only multiplying this fraction times 1. I could do that one too, but it doesn't really matter when you're multiplying by 1. So the thing is, I'm going to distribute this into here, into there, and then this one just gets multiplied there on the bottom. So the cosine squared x times the 2 is 2 cosine squared x. The cosine squared x times this fraction is sine squared x, because the cosine squareds cancel out. That was why I chose cosine squared, right? And likewise here, the cosine squareds cancel out. You just get a 1 on the bottom here. So that all looks like that. And then dividing by 1, of course, is just leaves it what it is. So I've got 2 cosine squared x plus sine squared x minus 1. Now, again, this is a matter of getting used to identities. And one of the identities is the Pythagorean one, which is sine squared x plus cosine squared x equals 1. It's close. I got 2 cosine squared x here. So I'm actually inclined to think, well, there's a couple different ways I can think of it. I also see a sine squared x minus 1. So sine squared x minus 1, if I rewrote that, actually, I'll do this 2 different directions. So the sine squared x minus 1, I'm looking at this saying, if I leave the sine squared x where it is, subtract the 1 over here, and subtract the cosine squared x over to the other side, then I'd have sine squared x minus 1 is equal to negative cosine squared x. So this bit right here, I could turn into a negative cosine squared x. So I've got 2 cosine squared x minus cosine squared x, which is just leaving 1 cosine squared x left. So it looks like this boils down to just cosine squared x. The other way I see doing this is to take that 2 cosine squared x and write it as cosine squared x plus cosine squared x, because that's what 2 of them means. You got 2 of them added together. And then you've still got the plus sine squared x and the minus 1. But now, the cosine squared x plus sine squared x, well, that's the same as 1. So I've got cosine squared x plus 1 minus 1. Well, the plus 1 and the minus 1 go away, and we end up back over here. Okay. So that was the way I probably would have done it myself when I was a student. I need to plug in. Okay, after a quick pause to plug myself in, I'm back again. So we just did it that way using sines and cosines. Once you get more familiar with more of the identities, you see other things to do. This is something I never would have seen as a student, just because I knew that I could always work with sines and cosines, and I just stuck with them. Anytime I had something that didn't have sines and cosines in it, I would convert to sines and cosines. But see, now I look at this thing and I think, oh, I've got secants and tangents. Those go together as nicely as sines and cosines do, because we did have the identity that sine squared x plus cosine squared x equals 1, but if I divide everything here by cosine squared x, the sine squared x divided by cosine squared x is tangent squared x. Cosine squared x divided by cosine squared x is 1, and 1 divided by cosine squared x is secant squared x. So this is another one of the Pythagorean relationships. And I can see that 1 plus the tangent squared is equal to the secant squared. Well, I've got 2 plus the tangent squared. Well, goodness, if I've got 2 plus the tangent squared, I've got 1 plus the tangent squared. I can write this as 1 plus the tangent squared x over the secant squared x minus 1. And so the 1 plus the tangent squared x, now it looks just like that, and I can replace it with the secant squared x. So I've got 1 plus the secant squared x all divided by the secant squared x minus 1. And now it's like, well, there's a couple ways I could proceed. I could get a common denominator, or I could just divide this in. I could write this as 1 over secant squared x plus secant squared x over secant squared x. And then the minus 1 is still out there. Well, this right here is equal to 1, and I've got a minus 1 over there, so those cancel out, and I'm left with 1 over secant squared x, which is cosine squared x, which I think is the same thing I got up above. If I zoom out a little bit here, yeah, we got cosine squared x. So depending on what identities you're most familiar with, it may determine, you know, which order, which direction you go in. But anything, as long as you're doing legal algebra, you're fine. I think this is what makes working with trig functions problematic for a lot of people, is because there's so many options that you have. It's like, well, that's also what makes it great, that you have so many options. So the idea is to get used to more and more of these identities so that you have them available to you when you're trying to do some algebra with trig functions, and you know what you can do. What are your options? So anyway, there's a couple different ways to do that problem.